Welcome to Part 2 of Customer Churn Analysis and Prediction using AI and Machine Learning. What a ride it's been! And we're just getting started. Look at how far we've come already. Till now, we loaded and explored the dataset like true data detectives. Transformed categorical variables into machine-friendly numbers through smart feature engineering. Visualized the hidden relationships between features using a vibrant correlation heat map. We've laid a solid foundation for building powerful predictive models, and trust me, the best is yet to come. What's coming next? Get ready to level up your data science game because we're diving headfirst into deeper EDA, uncovering more insights, spotting trends, and maybe even finding a few surprises. Train test splitting, preparing our data for modeling by splitting it into training and testing sets. Machine learning models galore. Applying powerful classification algorithms like Logistic Regression, Random Forest, and XGBoost to predict customer churn. Model evaluation, finding out which model performs best using metrics like accuracy, precision, recall, and F1 score. You won't want to miss this, it's where the magic really happens. Every line of code we write brings us closer to solving one of the most critical challenges businesses face today: predicting and preventing customer churn. Whether you're a beginner or brushing up on your skills, you're already on your way to becoming a churn-busting data wizard. Subscribe to Cognitutor so that you can take advantage of all the upcoming hands-on projects and tutorials. Let's get started. Unveiling hidden relationships. Exploring correlations with a heat map. So, in our last video, we transformed our dataset by encoding all categorical variables, making it entirely numerical and ready for analysis. Now, it's time to dive deeper into the data and uncover hidden relationships between features. To do this, we'll use a powerful visualization tool called a heat map. This colorful chart will reveal correlations between different variables, helping us identify which features might be most important for predicting customer churn. Let's get ready to decode these patterns. Why does it matter? Understanding the relationships between features is crucial in machine learning. A heat map of correlations helps us identify which features are strongly related to the target variable, detect multicollinearity, which can affect model performance, prioritize features for modeling by focusing on those with the strongest relationships. By visualizing these correlations, we gain valuable insights that guide our feature selection and pre-processing steps. What to expect in this step? In this step, we'll calculate the correlation matrix using df.corr. Visualize the correlations using a heat map with Seaborn. Interpret the heat map to understand which features are positively or negatively correlated with each other and with the target variable. This step will provide a clear picture of how different features interact and help us make informed decisions about which features to include in our models. Fun fact: did you know? The color intensity in a heat map represents the strength of the correlation. Positive correlations are typically shown in warm colors, while negative correlations are shown in cooler colors. The closer the correlation coefficient is to +1 or -1, the stronger the relationship. A correlation close to 0 indicates no linear relationship between the variables. Real-life example related to this step. Imagine you're working for a telecom company, and you need to predict which customers are likely to churn. By creating a heat map of correlations, you might discover that tenure is strongly negatively correlated with churn. This means that customers who have been with the company for a longer time are less likely to leave. Armed with this insight, you can focus on retaining long-term customers by offering them special promotions or loyalty programs. Similarly, if you find that monthly charges is positively correlated with churn, you might investigate whether high monthly bills are driving customers away. This could lead to strategies like introducing more affordable plans or offering discounts to at-risk customers. Mini quiz. Quiz time. Let's test your understanding of correlation heat maps, students. Question 1. What does a strong positive correlation indicate in a heat map? A. Two variables move in opposite directions. B. Two variables move in the same direction. C. There is no relationship between the variables. Question 2. Why is detecting multicollinearity important when building a machine learning model? A. Because it makes the model run faster. B. Because it ensures all features are unique. C. Because highly correlated features can confuse the model. Drop your answers in the comments. I am excited to hear your thoughts. Here's a quick cheat sheet for interpreting correlation heat maps. 1 close to +1 means strong positive correlation. 2 close to -1 means strong negative correlation. 3 close to 0 means no linear relationship, means variables are independent. A pro tip for you: when interpreting a correlation heat map, focus on the target variable to identify which features are most strongly related to it. Be cautious of multicollinearity. If two features are highly correlated, consider removing one to avoid redundancy in your model. Remember that correlation does not imply causation. Just because two variables are correlated doesn't mean one causes the other. So, what's happening in this code? The code block performs the following tasks. Calculate correlation matrix. Uses the .corr method to compute the Pearson correlation coefficients between all numerical columns in the dataset. This produces a symmetric matrix where each cell represents the correlation between two variables. Visualize correlation matrix. Creates a heat map using Seaborn's SNS.heatmap function. Sets the figure size to ensure the heat map is large enough to read. Adds annotations to display the correlation coefficients in each cell. Includes a color bar to show the correlation scale. Uses the plasma color map, where warmer colors represent positive correlations and cooler colors represent negative correlations. By visualizing the correlation matrix, we can quickly identify patterns and relationships between features. The heat map shows the correlation coefficients between all pairs of numerical features in the dataset. Here's how to interpret it. Color intensity. Warm colors indicate positive correlations. Cool colors indicate negative correlations. Neutral colors indicate weak or no correlation. Correlation coefficients. Values close to +1 indicate a strong positive correlation. Values close to -1 indicate a strong negative correlation. Values close to 0 indicate no linear relationship. Key observations from the heat map. Strong positive correlations. Tenure and total charges. Customers who have been with the company longer tend to have higher total charges, indicating a strong positive relationship. Monthly charges and total charges. Higher monthly charges contribute to higher total charges over time. Strong negative correlations. Senior citizen and churn. Senior citizens appear to have a slightly negative correlation with churn, suggesting they might be less likely to leave. Contract and churn. Customers with longer contracts have a negative correlation with churn, indicating they are less likely to leave. Moderate correlations with churn. Tenure. Customers with shorter tenures are more likely to churn. Monthly charges. Higher monthly charges are moderately correlated with churn, suggesting that expensive plans might drive customers away. Paperless billing. Paperless billing has a moderate positive correlation with churn, possibly indicating that customers who prefer paperless billing are more likely to leave. Multicollinearity check. Look for cells with very high positive correlations between independent variables. For example, tenure and total charges have a strong positive correlation, which might indicate multicollinearity. This could affect model performance, so we might consider addressing it later. Some insights are: the heat map provides valuable insights into the relationships between features. Key drivers of churn. Features like tenure, monthly charges, and contract appear to have significant correlations with churn. These could be critical predictors in our churn prediction model. Redundant features. High correlations between tenure and total charges suggest potential multicollinearity. We might need to address this by selecting one of these features or applying dimensionality reduction techniques. Unexpected patterns. Some correlations might surprise us, such as the slight negative correlation between senior citizen and churn. This could prompt further investigation into why senior citizens are less likely to churn. Unveiling the shape of our data. Exploring feature distributions. After encoding categorical variables and exploring correlations, it's time to take a closer look at how each feature is distributed. By visualizing the distributions of our features, we can uncover patterns, identify outliers, and gain insights that will guide our modeling decisions. Let's dive in and see what stories these distributions have to tell. Understanding the distribution of your features is crucial for several reasons. Identify skewness. Some machine learning algorithms perform better with normally distributed data. If a feature is heavily skewed, you might need to apply transformations like logarithmic or box-Cox to normalize it. Detecting outliers. Extreme values in a distribution can significantly impact model performance. Visualizing distributions helps you spot potential outliers early on. Feature insights. The shape of a distribution can reveal important characteristics about the data. For example, a bimodal distribution might indicate two distinct groups within the data. By exploring these distributions, we ensure that our data is clean, well understood, and ready for modeling. What to expect in this step? In this step, we'll use Seaborn's dist plot or displot in newer versions to visualize the distribution of each feature. Create a grid of subplots to display all feature distributions in one go. Interpret the shapes of the distributions to identify skewness, multimodality, and other patterns. This step will provide a comprehensive view of how our data is structured, helping us make informed decisions about preprocessing and feature engineering. Fun fact: did you know? The shape of a distribution can tell you a lot about the underlying data. For example, a normal distribution bell-shaped curve indicates that most values cluster around the mean, with fewer extreme values. A skewed distribution lopsided bell curve suggests that the data is not symmetric, with a longer tail on one side. A bimodal distribution two peaks indicates that there are two distinct groups or clusters within the data. Understanding these shapes helps you decide whether to apply transformations or treat certain features differently during modeling. Real-life example related to this step. Imagine you're working for a telecom company, and you're analyzing customer data to predict churn. By visualizing the distribution of monthly charges, you notice that most customers pay a similar amount, but there's a long tail of high-paying customers. This could indicate that high monthly charges might be driving some customers away. Armed with this insight, you might decide to focus on retaining high-value customers by offering them special discounts or loyalty programs. Similarly, if you see a bimodal distribution in contract, many customers have either month-to-month contracts or two-year contracts. You might explore why customers choose different contract lengths and how it relates to churn. Mini quiz time. Let's test your understanding of feature distributions, students. Question 1. What does a skewed distribution indicate about the data? A. The data is perfectly symmetrical. B. The data has a longer tail on one side. C. The data is uniformly distributed. Question 2. Why is it important to visualize feature distributions before modeling? A. To make the code run faster. B. To detect outliers and understand data characteristics. C. To impress your colleagues. Drop your answers in the comments. I am excited to hear your thoughts. A cheat sheet for you. Normal distribution, symmetrical, bell-shaped curve. Most values cluster around the mean. Skewed distribution, asymmetrical with a longer tail on one side. Data is not evenly spread. Bimodal distribution, two distinct peaks may indicate two separate groups in the data. Uniform distribution, flat-shaped values are evenly distributed with no clear pattern. Use histograms or density plots. SNS.dist plot to visualize distributions. Skewness can be handled using transformations like log or box-Cox. Outliers and extreme values can be spotted visually in skewed distributions. Feature distributions help decide pre-processing steps and model choices. The output shows multiple subplots, each displaying the distribution of a different feature. Here's what we can observe from the distributions. Key observations. Numerical features. Monthly charges and total charges, both show right-skewed distributions, indicating that most customers have lower charges, while a few have very high charges. Tenure shows a slightly right-skewed distribution, suggesting that most customers have shorter tenures, but there are some long-term customers. Binary/categorical features. Features like gender, partner, dependence, etc., show bimodal distributions with peaks at 0 and 1, reflecting binary categories. Features like payment method and internet service also show distinct peaks, indicating different categories. Other observations. Churn shows a bimodal distribution with peaks at 0 non-churned and 1 churned, confirming the binary nature of the target variable. Contract shows 3 distinct peaks, corresponding to month, 1 year, and 2 year contracts. Patterns to note. Skewness. Features like monthly charges and total charges are right-skewed, which might require transformations. Outliers. Some features might have extreme values that could be worth investigating further. Imbalance. The churn distribution shows that non-churned customers 0 are more frequent than churned customers 1, indicating class imbalance. By visualizing the distributions, we've gained valuable insights into the structure of our data. Skewed features, monthly charges and total charges might benefit from transformations to normalize their distributions. Binary features. Most binary features like gender, partner are balanced, but churn shows an imbalance, which we'll need to address later. Categorical features. Features like payment method and internet service have distinct categories, which aligns with our expectations. These observations will guide our pre-processing steps and help us build more accurate models. Balancing the scales. Tackling class imbalance with oversampling. In our last step, we explored the distributions of all features and noticed something important: our target variable churn is imbalanced. That means one class non-churned customers has way more samples than the other churned customers. This can trick machine learning models into ignoring the minority class. But don't worry, today, we're going to fix that using a technique called oversampling. Let's level the playing field and make sure our model learns from both classes equally. Why it matters. Class imbalance can severely impact model performance. Imagine training a model where 90% of your data says no churn. The model might just learn to always predict no churn, and you'd never know it failed completely on the important minority class. By balancing the dataset, we ensure the model pays attention to both churned and non-churned customers. Evaluation metrics like precision and recall become more meaningful. Our predictions are more reliable in real-world scenarios. What to expect in this step? In this step, we'll identify the majority and minority classes in the churn column. Use oversampling to increase the number of minority class samples. Combine the resampled minority class with the majority class. Confirm the new balanced class distribution with .value counts. This is a crucial pre-processing step before building classification models. Fun fact. Did you know? There are 2 main ways to handle class imbalance. Oversampling, increase the number of minority class instances like we're doing here. Undersampling, reduce the number of majority class instances. Both have pros and cons, but oversampling is often preferred when data is limited, as it doesn't throw away valuable information. 5 real-life example related to this step. Imagine you're working for a telecom company trying to detect fraudulent activity. Only 1% of transactions are fraudulent, the rest are legitimate. If you train a model without balancing, it could achieve 99% accuracy by labeling everything as not fraud, which is useless. By applying oversampling, you give the model enough examples of actual fraud cases to learn from, helping it detect suspicious behavior effectively. Mini quiz time. Let's test your understanding of handling class imbalance, students. Question 1. Why is class imbalance a problem in classification tasks? A. It makes the model biased toward the majority class. B. It increases computation time. C. It reduces the number of features. Question 2. What does oversampling do? A. Removes samples from the majority class. B. Adds more samples to the minority class. C. Changes the labels of the data. Drop your answers in the comments. I am excited to hear your thoughts. A cheat sheet for you. Class imbalance. One class dominates the dataset, leading to poor model performance on the minority class. Oversampling, technique used to increase the number of minority class samples. Undersampling, technique used to reduce the number of majority class samples. Use case, oversampling is useful when the dataset is small and losing data isn't an option. Implementation, use resample from sclearn.utils for manual oversampling. Evaluation impact, balanced data improves metrics like recall and F1 score. Best practice, always balance your data before splitting into train/test sets. Pro tip for you. Always apply balancing techniques before splitting your data into training and testing sets. If you balance after splitting, you risk leaking information from the test set into the training process, which can lead to overfitting and overly optimistic performance estimates. What's happening in this code? The code block performs the following tasks. Import resample. Imports resample from sclearn.utils, a handy utility for sampling datasets. Split into majority and minority classes. Separates the dataset into two data frames. df majority contains all rows where churn equals 0 non-churned customers. df minority contains all rows where churn equals 1 churned customers. Oversample minority class. Uses resample to artificially increase the size of the minority class to match the majority class and samples equals 5163. Replace equals true allows random sampling with replacement, i.e., duplicates may occur. Random state equals 42 ensures reproducibility. Recombine classes. Combines the upsampled minority class with the majority class using pdconcat. Check class balance. Uses .value counts to confirm that both classes now have equal representation. The output shows the updated count of each class in the churn column. Before, the original dataset had many more non-churned customers churn equals 0 than churned ones churn equals 1. After oversampling, both classes now have exactly 5,163 samples, making the dataset perfectly balanced. This ensures that any model we build will learn patterns from both churned and non-churned customers equally, improving its ability to make accurate predictions. By balancing the dataset through oversampling, we've taken a major step toward building fair and effective classification models. Now, when we train our models, they won't be biased toward predicting only the majority class. This will lead to better performance, especially in terms of identifying churned customers, which is exactly what businesses care about. Training our models, let the battle begin. In this step, we're entering the final frontier of modeling, training multiple machine learning algorithms on our balanced dataset and seeing which one reigns supreme in predicting customer churn. We'll split our data into training and testing sets. Apply feature scaling so all models get a fair chance. Train 9 powerful classification models, including Logistic Regression, Random Forest, XGBoost, CatBoost, and more. Evaluate their performance using accuracy scores. This is where your hard work pays off. Let's see how good our models really are. Why it matters. Training and evaluating different models helps us understand which algorithm performs best on our specific dataset. Compare strengths and weaknesses of different approaches. The tree-based vs linear vs ensemble. Choose the best model for deployment or further optimization. This is the heart of any machine learning project, and it's super fun too. What to expect in this step? In this step, you'll learn how to split data into training and testing sets. See how to apply feature scaling using standard scaler. Discover how to train and predict with 9 different classifiers. Understand how to evaluate accuracy for each model. Get ready to pick a winner and move on to deeper evaluation. Fun fact: did you know? Some ML models like KNN and SVM are heavily affected by feature scales, while tree-based models like Random Forest and XGBoost are scale invariant. That's why we scale features only when necessary, not all models need it. Real-life example related to this step. Imagine you're working at a telecom company and have built a churn prediction system. You train several models, and after testing, you find that Random Forest gives the highest accuracy. But wait, what if it's overfitting? What if it fails to detect actual churners? That's why we don't just look at accuracy, but in this step, we're starting with accuracy as our first checkpoint before diving into more advanced metrics like precision, recall, and F1 score. Mini quiz time. Let's test your understanding of model training and evaluation. Question 1. Why do we scale features before training some models? A. To make plots prettier. B. Because some models are sensitive to feature magnitudes. C. Just for fun. Question 2. Which of these models is not affected by feature scaling? A. KNN. B. SVM. C. Random Forest. Drop your answers in the comments. I am excited to hear your thoughts. Another cheat sheet for you. Use train test split to split data into train and test sets. Scale features using standard scaler before using models like KNN, SVM, or Logistic Regression. Tree-based models like Random Forest, XGBoost, LightGBM, CatBoost do not require scaling. Accuracy is a good starting metric, but it doesn't tell the full story, especially for imbalanced data. Always evaluate models on test data, never on training data. Top performing models in this run: Random Forest, CatBoost, LightGBM, XGBoost. Beware of overfitting. High training score, low test score equals bad news. Pro tip for you: when comparing multiple models, don't just rely on accuracy, especially for classification problems. Use cross-validation to ensure robustness. Keep track of results using a data frame or dictionary for easy comparison. Save the best model using Joblib or Pickle for future use. 9. What's happening in this code? The code block performs the following tasks. Define features and target. X. All columns except churn. Y. The target variable churn. Train test split. Uses train test split to divide the data into 80% training and 20% testing sets. Feature scaling. Applies standard scaler to standardize numerical features by removing the mean and scaling to unit variance. Model selection and instantiation. Imports and initializes 9 classification models. Logistic regression. Random forest. Gradient boosting. XGBoost. SVM. KNN. Naive Bayes. LightGBM. CatBoost. Model training. Fits each model on the scaled training data. Predictions. Makes predictions on the scaled test data. Accuracy evaluation. Calculates accuracy scores for each model. Prints them out for easy comparison. Key observations. Random Forest performed the best with an impressive 90.7% accuracy. CatBoost and LightGBM followed closely behind 84%. Naive Bayes had the lowest performance, 75.7%. While accuracy is a great starting point, remember that it can be misleading if the classes aren't perfectly balanced, even though we did balance here. So, in the next step, we'll dive deeper into precision, recall, and F1 score to understand how well each model identifies churned customers. From the results, Random Forest emerged as the top performer, no surprise there. It's known for strong performance on tabular datasets and handles both numerical and categorical data well after encoding, of course. However, accuracy alone isn't enough. For example, a model might predict most people as not churned even if they actually are. We need to check how many churned customers were correctly identified. That's where recall comes in. So don't celebrate just yet, the real battle begins now. Digging deeper. Unveiling the confusion matrix for our best model. In our last step, we trained multiple machine learning models and found that random forest emerged as the top performer with an impressive accuracy of 90.7%. But wait, accuracy alone doesn't tell the whole story. To truly understand how well our model is predicting churn, we need to dive deeper into its performance using tools like the confusion matrix. In this step, we'll visualize the confusion matrix to see how many true positives, true negatives, false positives, and false negatives our random forest model produced. Interpret the results to gain insights into where our model excels and where it struggles. Get ready to uncover some exciting patterns. Let's decode the confusion matrix and see what stories it has to tell. Why it matters. The confusion matrix provides a more detailed view of a model's performance compared to accuracy alone. It helps us answer critical questions like: how many actual churned customers did the model correctly identify true positives? How many non-churned customers were incorrectly flagged as churned false positives? How many churned customers were missed by the model false negatives? By analyzing these metrics, we can identify areas where the model needs improvement. Understand whether the model is biased toward predicting one class over another. Make informed decisions about hyperparameter tuning or feature engineering. This step is crucial for building trust in our model and ensuring it performs well in real-world scenarios. So, in this step, we'll use confusion matrix from sklearn.metrics to compute the confusion matrix for the random forest model. Visualize the confusion matrix using a heat map to make it easier to interpret. Analyze the results to understand the model's strengths and weaknesses. This will give us a clearer picture of how well our random forest model is distinguishing between churned and non-churned customers. Fun fact: did you know? The confusion matrix gets its name because it shows how the model confuses different classes. For example, if a customer who actually churned is predicted as non-churned, that's a false negative. The model got confused and missed the churn. Similarly, if a non-churned customer is predicted as churned, that's a false positive. The model got confused and raised a false alarm. Understanding these confusions helps us improve the model and avoid costly mistakes in real life. Real-life example related to this step. Imagine you're working for a telecom company, and your random forest model predicts that a customer will churn. If the model produces a false positive, it might trigger unnecessary retention efforts like offering discounts or promotions for a customer who wasn't going to leave anyway. On the other hand, if the model produces a false negative, it might miss a customer who was about to churn, leading to lost revenue. By analyzing the confusion matrix, you can identify such issues and take corrective actions, like adjusting the model's threshold or gathering more data to improve predictions. Mini quiz time. Let's test your understanding of the confusion matrix, students. Question 1. What does a false positive represent in the context of churn prediction? A. Predicting a churned customer as non-churned. B. Predicting a non-churned customer as churned. C. Correctly predicting a churned customer. Question 2. Why is the confusion matrix important? A. Because it shows the overall accuracy of the model. B. Because it reveals how the model misclassifies different classes. C. Because it makes the code run faster. Drop your answers in the comments. I am excited to hear your thoughts. What's happening in this code? The code block performs the following tasks. Import metrics. Imports confusion matrix from sklearn.metrics. Compute confusion matrix. uses confusion matrix test, refpred to calculate the confusion matrix for the random forest model's predictions refpred against the actual labels y-test. Visualize confusion matrix. Creates a heat map using sns.heatmap to display the confusion matrix. Adds annotations a0 equals true to show the exact values in each cell. Sets the title as heat map of confusion matrix. By visualizing the confusion matrix, we can easily spot patterns and evaluate the model's performance. The output shows the confusion matrix for the random forest model. Key observations. True positives, the model correctly identified 1,000 churned customers. True negatives, the model correctly identified 860 non-churned customers. False positives, the model incorrectly predicted 150 non-churned customers as churned. False negatives, the model incorrectly predicted 46 churned customers as non-churned. From the heat map. The dark cells top left and bottom right represent correct predictions TP and TN. The lighter cells top right and bottom left represent errors FP and FN. Insights. The model is quite good at identifying non-churned customers high TN. However, it struggles slightly with identifying churned customers low TP relative to FP and FN. Insight. The confusion matrix reveals that while our random forest model performs well overall, there are still areas for improvement. False positives, the model flags too many non-churned customers as churned, which could lead to unnecessary retention efforts. False negatives, the model misses some churned customers, which means potential revenue loss. These insights will guide us in fine-tuning the model or exploring additional metrics like precision, recall, and F1 score. We're on fire. Part 2 wrap-up and what's coming next in Part 3. Wow, look at everything we've accomplished in Part 2 of our Customer Churn Prediction project. We dug deep into the data with exploratory visualizations to understand feature distributions. Tackled a very real-world problem class imbalance using smart oversampling techniques. Split our data and scaled our features like pros. Trained 9 powerful classification models, from Logistic Regression to CatBoost. Compared their performance using accuracy scores, and found that random forest came out on top. Visualized the confusion matrix to go beyond accuracy and peek under the hood of our best model. This is no small feat. You're officially building models that businesses would use to retain customers and boost revenue. But hold on, the best is yet to come. In Part 3, we're going full-on data scientist mode as we dive into advanced model evaluation. Here's what's on the menu. Classification report. Break down the random forest model's performance using precision, recall, F1 score, and support, giving us a much clearer picture than accuracy alone. SHAP analysis, Shapley additive explanations. Unlock the black box of machine learning by understanding which features are driving predictions for churn. This is gold when explaining your model to stakeholders or managers. Cross-validation scores. Test the robustness of our model across different subsets of data to ensure it's not just lucky on one split. More visualizations and interpretations. Because seeing really is believing, and storytelling with data is just as important as building the model itself. Final thoughts. You're not just writing code, you're solving a real business challenge that companies spend millions trying to crack. With every line you write, you're getting closer to becoming a data-driven decision maker who can predict customer behavior and help businesses grow. So pat yourself on the back, you've earned it. And get ready for next video, where we'll turn our high-performing model into an insight-generating powerhouse. See you there, future data legend.